I wanted to tell you a little bit about air quality and atmospheric chemistry because it fits really nicely in with this chemical kinetic stuff we're discovering, mostly with mechanisms and activation energies and so on. But the field of atmospheric chemistry and air pollution was really created by chemical kineticists, which is what I have my training in. This is what I did my PhD in. So I want to tell you a little bit about this because most of us are Californians, and additionally, this phenomenon was discovered was discovered in California. Okay, so let's get into it. So you can see I've got a hideous mess of chemistry going on here, but let's start from the beginning. So you all are very familiar with this reaction. I made you calculate a bunch of stuff about this reaction on exam number 1, if you recall. And if you recall, this reaction is important in tailpipes, okay? So we recognize N2 and O2, right? As I'm sitting here breathing in a bunch of N2 and O2, they don't react very readily at room temperature. But if we add heat, right, such as in a tailpipe or in a combustion reaction, it drives this reaction to form NO, okay? And NO is where the story all starts. So let's talk about NO, and let's talk about it starting right here in this scheme, okay? So we also now have to talk about VOC. That stands for volatile organic compound. And volatile does not mean that it's reactive. Volatile means that it's a gas, that it has a high vapor pressure. It wants to evaporate, okay? So these VOCs also come from tailpipe emissions or other industrial chemical facilities, okay? VOCs can also come from plants and vegetation. So if you've ever been into the redwood forest, which I assume you have, and you smell that lovely like pine fresh smell, those are also from volatile organic compounds, okay? But as it turns out, this phenomenon is especially important when you have both NO and VOC, okay? So VOCs can react with OH radical. So this is, I'm gonna put a little dot right there. OH radical occurs naturally. There is a natural creation of the OH radical in Earth's atmosphere, very much like there's a natural depletion of ozone in Earth's atmosphere, but it's balanced by environmental cycles and ecological cycles, okay? So without human intervention, we would have some VOC and some OH radical, albeit at very, very small concentrations, okay? So when the VOCs and the OH radicals combine, it forms this oxidized compound, RO2. So the R is just an abbreviation for like the molecular structure of the VOC to begin with. And without getting into too much details, basically this is oxidation chemistry. So the VOC gets oxidized into this RO2 thing, and now this is where the chemistry goes crazy. Because RO2 will react with NO and make this RO thing, which is a radical. It's an unstable compound, but you notice that it goes back and makes NO2. NO2 reacts with sunlight to give us back NO as well as ozone. And this ozone is now at ground level. This is not like upper atmosphere ozone. This is ground level ozone. And ozone can also react with VOCs to make this cycle go round as well, okay? Importantly, what you're noticing, what you should notice here is the NO gets recycled to NO2, but then the sunlight recycles it back to NO and ozone. And so that means these cycles will just keep going round and round and round and round. So to finish it off now, this RO will react with oxygen in the atmosphere, so O2. That makes carbonyl products. Don't worry so much about what that is. It's more oxidized organic materials. But now, as you can see what happens, a new cycle is created. This reaction of RO plus O2 will make HO2, which will then react with NO to form another NO2, another ozone, and another NO, and more HO2. So you can see here, the only inputs for this thing are VOCs and sunlight. And of course, some initial input of NO. And it just makes this chemistry go round and round and round and round. And why this is important, because these carbonyl products and these O3 can now react, and this goes on to make smog. Okay, so here I've got a lovely picture of the Los Angeles skyline. Those of you that live in LA or have been there, you are very familiar with the smog, like the crap brown layer of air, right? That's this smog chemistry that you're seeing unfold right before your eyes. And so if you look at this time profile now, you can see it starts at about 6 in the morning, NO concentration starts building. And if you think, why is that? Well, that's because traffic has started, right? Everybody's waking up, they're getting on the 405, and they're going to work. And so when that NO is building up, right, from the N2 and O2 reacting in the tailpipe to make NO, as you can see, NO leads to NO2 via these cycles right here, right? There's 2 of these NO to NO2 cycles for every 1 total reaction cycle. NO2 leads to the formation of O3. Of course, these VOCs are also building in concentration because in addition to NO coming out of the tailpipe emissions, these volatile organic compounds are getting spit out of tailpipes as well. And so finally, the VOC and the ozone react. And by the time it's the afternoon, or even a little bit earlier than that, you know, perhaps even around like the noon time, the smog has built enough that you can visibly see it. And the crazy part about this chemistry, you'll notice now all of these things are starting to decay, right? Well, by the time it's the evening and the sun has gone down, all of this chemistry gets shut off and everything terminates. The next day starts, the sun comes up, everybody goes to work, and all this chemistry starts forming again. So this is a daily cycle. A couple of factors that improve this chemistry: when it rains, all of these compounds get washed out of the atmosphere. And you might have noticed that if you live in LA on rainy days, the air is just beautiful and pristine and clear. And that's because the rain is actually washing this chemistry straight out of the atmosphere. This chemistry is still going on, but water is helping curtail that chemistry. Also, there's another really important factor that came out of the discovery of this chemistry, and that's the catalytic converter. So let's talk about that, okay? So this was created in about 1975 as a result of all of this chemistry being discovered in the greater Los Angeles area and people just getting sick from the air. So the way this works now are NO gets produced from the combustion reaction. But now before that air gets sent on out to the tailpipe, it has to pass through your catalytic converter. Well, the catalytic converter will allow NO molecules to line up in this way that spits back out into an O2. So it converts the NO back to into an O2. And just that one effect, right? When you take out the NO from this cycle, it does a really good job of shutting down this cycle completely. Now, of course, we can't eliminate all of the NO that comes out of these tailpipe emissions. And there's a lot of legacy vehicles on the road, older vehicles whose catalytic converters aren't nearly as efficient as newer vehicles. So I've said it before and I'll say it again. Get your car smog checked, because you're helping improve the air quality by getting your car smog checked. And the last thing that I'll end up with is by saying that when we use fundamental science, such as chemical kinetics, to understand the environment, we can arrive at laws and legislature that make sense and that can improve our world that we live in. So for example, if we look here, 1975, this was the creation of the EPA. The Environmental Protection Agency was started around 1975, as well as the mandate that all new cars had to have catalytic converters. Well, so now if you look, there's two things going on in this graph. Number of stage 1 smog alert days and the base and maximum ozone concentration. And that ozone concentration is a good proxy for smog. So we'll say proxy for smog. Additionally, these number of stage 1 smog alert days, so a stage 1 smog alert day is now what we would associate with a red AQI day. So if you've paid attention when we've had those forest fires and you see the AQI, which is the air quality index, when that number starts spiking way up, like values of around 300 or 400 or so, that's what we previously called a stage 1 smog alert. And in a stage 1 smog alert, children, elderly, and people affected by these types of things, so people with cardiovascular issues, have to go inside. The air is literally toxic for you if you're in one of those categories. And if you look at 1975, there was like 120 of those days in 1 year. That means every third day there was a toxic event going on out there where literally the air was toxic. Okay? So what happened? Well, the EPA was invented and they said all cars must have catalytic converters. And look what happened. Air pollution went way down to the point now where in the year 2000, there's only been like 1 or 2 stage 1 smog alerts due to air pollution. Now, of course, we've had stage 1 smog alerts due to forest fires. That's a whole other issue. All the same, what's impressive to me is I looked this up on LA County's website. In 1998, which was probably about the time most of you were born, I'm going to guess, around the late 90s, maybe early 2000s, there was 4.8 million registered automobiles just in LA County. That's not like trucks or boats or whatever, right? This is just personally registered automobiles. 4.8 million in one county. And you wonder why there's a smog problem, right? Here's what's really impressive about that, though. Over the next 20 years, hardly any stage 1 smog alerts. And look, we put an extra 1.5 million cars on the road. That's really, really impressive, right? Think about that. We put another 1.5 million automobiles on the road just in LA County without affecting air pollution at all. And that is because you are required to get your car smog checked. You're required to have a catalytic converter in it. And additionally, over these past 20 years, there's been enormous improvements in technology and efficiency in automobiles. So even though we often think of automobiles as producing, carbon dioxide and contributing to climate change, they also contribute to air pollution. And so I like to think of this as a 2-for-1. If you do the hard work to improve air pollution, simultaneously you're doing the hard work to improve climate change. So take-home story from this is environmental legislation works when we listen to the scientists. And that's a big problem going on in politics right now, as you may or may not be aware of. There's a lot of our political leaders out there who are just not listening to the science. And I'm fearful of another thing like this happening where now our air pollution is going to go back up again. So we got to keep fighting to get our politicians to listen to the scientists and make laws based off of fundamental scientific facts because it works. Here's the evidence that it works. And California has been a worldwide leader in this front. Okay, folks, that's all I'll say on kinetics. I'm happy to talk about this in much more detail. I love this stuff. It's what I do. It's what I'm passionate about. So please hit me up if you want to learn more about the air pollution phenomenon in greater Southern California. Okay, hasta luego.